Hello, this is Maureen Julian. This is Chapter 3, Part 2, 3 Dimensions. So far we've just had 2 dimensions, and now we're going to add a 3 dimension, and voila, look at the difference. Oh yes, we can do it with giraffes too. Now the first thing we're going to do is we're going to apply a lot of things that we've learned in 2 dimensions, and we're going to apply them to 3 dimensions. For example, in 2 dimensions we found that for a for periodicity or crystallographic symmetry, we're only allowed 1, 2, 3, 4, and 6 dimensional rotations, or we're only allowed the identity 2-fold, 3-fold, 4-fold, and 6-fold proper operations, and that's true also in 3 dimensions. When we come to 3 dimensions, we're going to also have an XYZ world, and we're going to have a 3x3 matrix instead of the 2x2 matrices for 2 dimensions. Other things are quite similar. First of all, the stereographic projections are identical. The point stereographic projections are similar, except that the point becomes interior to the circle, and we're going to see why that's the case in just a moment. Here's the point groups 1, 2, 3, 4, and 6. They're cyclic point groups. And here are the crystal systems. We have hexagonal and tetragonal, which we know about already. And then if there's a 3-fold involved, we call it, if it starts with a 3-fold, we call it a trigonal. Then we have the 2-folds associated with the leading 2-fold with the monoclinic, or the single 2-fold with the monoclinic, and the triclinic, the identity. An overview now for the improper operations are going to be the n-fold roto-inversions. In 3 dimensions, there are 5 improper operations: 1 bar, 2 bar, which we're going to see is equal to m, 3 bar, 4 bar, and 6 bar. All of these operations change handedness, and the determinants of the associated matrices are going to be equal to 1 minus 1 rather. Each of the operations is associated with a corresponding cyclic point group that has a single generator. So here we have the inversion point, and if we put the origin at right in the center here, then we have XYZ going into X bar, Y bar, Z bar. Here's an example of a molecule. Here's the copper in the center here, and you can see the carbon oxygen goes into a carbon oxygen, and we have an inversion point, and only an inversion point in this molecule. The inversion symmetry operation involves a point called the inversion point, and if the origin is placed at the inversion point, the operation takes the point at XYZ into a point at X bar, Y bar, Z bar. The matrix for the inversion is 1 bar is equal to 1 bars all down the diagonal. The determinant of that matrix, of course, is, yes, come on, minus 1. So we have a change of handedness. In 3 dimensions, there are 5 improper operations. Multiply each rotation operation by an inversion operation to get the 5 improper rotations. So we're going to get 1 bar, 2 bar, which we're going to show as a mirror, or M, 3 bar, 4 bar, and 6 bar. So a roto-inversion, this is the definition, is a 3-dimensional symmetry operation composed of a rotation followed by an inversion operation. Here is the setup for the roto-inversions. We have the inversion, and we always have to have, since it's always going to have an inversion multiplied by, we're going to have to put some sort of an indication of where that is. So here's the point at 0, 0, 0, takes XYZ into X bar, Y bar, Z bar. And here we have the 3 bar, which is 3 bar plus, which means you rotate counterclockwise by 120 degrees and put yourself through an inversion point. And these are the coordinate transformation, and here's the corresponding matrix. If you compare the proper operations with the improper operations, you see that we're just multiplying this operation by minus 1, minus 1, minus 1. Notice we're along the rotations are along the z, along for 3 plus, 4 plus, and 6 plus. So for 3 bar plus, 4 bar plus, and 6 bar plus, we can see that we just simply multiply these various matrices by minus 1. So we have this as this becomes plus 1 over here, this becomes minus 1, this becomes plus 1, and the corner down here becomes minus 1. The all of these matrices will have a determinant of minus 1, so they change, so the particular operations change handedness. Notice we're following the notation in the international tables where we have the twofold along the y-axis here, but in this case we have the mirror along the xy with the z perpendicular to that mirror along here. So that's why these two look a little bit different. The mirror is, we show a picture of our dog Rufo, and he's got a mirror right through him, and his right paw, which is at x, y, and z, here's the y-axis, goes through the mirror and comes out at x, y bar, z. Here's an example of perchloric acid where you have a mirror plane coming down through here, and you can see the three-dimensional form of it here. You can see a mirror plane here, but it just looks like a 2D mirror, so I thought I'd show you a little tilted one. And what I want to show here is the relationship between 2 bar and m. So if we get 2 bar, what does that mean? Well, we take 2 and we multiply it by 1 bar, and we get this matrix. And now if we look at Rufo, we can see the transformation is xyz into x, y bar z, which has the following matrix here, and we can see these two matrices are identical. Therefore 2 bar is equal to m, and we're going to from now on we're going to be using m as our symbol, not 2 bar, but we can always think about it in the back of our mind. Now here's another place where we have a lot of similarities. So here's our graphic symbols. They're all the same. The symmetry operations look the same, but actually the symmetry operations, if you represent them by matrices, these are all 3 by 3 matrices. And when we come over here to the improper, or in this case we're selecting out the roto-inversions, here we have the mirror plane here, and now we also have 1 bar, which is represented by a tiny circle here, and it has 1 and 1 bar as the symmetry operations associated with it. 3 bar is going to have 1 3 plus 3 minus, and 1 bar 3 bar plus and 3 bar minus, and that's represented by a triangle because to represent the 3-ness. And then we can see that there's an inversion point. The 1 bar is here, and that's indicated by this little circle here, which is the center of that little circle there that we brought down. Now if you look at 4 bar and 6 bar, 4 bar doesn't have an inversion point, 6 bar does not have an inversion point, so it doesn't have that. That is not in the symbol. That's why it's not in the symbol, because it's not there. So the 4 bar we indicate by the 4, by the square pointed upward, and you can see it has a subgroup of 1 and 2, which is over here. So we put that twofold in the center here, and likewise with the 6 we have the subgroup of 1 3 plus 3 minus, and we put the little triangle in the center of the hexagon. The hexagon is for the sixness, and therefore we have this symbol. And we color all of these purple because their operations are half red and half blue, half red, half blue, half red, half blue associated with them. Now I suggest you go to chapter 8 and look in more detail at how I arrive at some of these colors. So now let's consider our 10 three-dimensional point group operations, or these are the cyclic groups, and these can be form 32 point groups, and those point groups are divided into 7 crystal systems. And we've seen some of them already. We can add to that the cubic and the orthorhombic, and here's all the Hermann-Morgan symbols, and those are all the combinations that you can get. The Hermann-Morgan combines these various symbols to give you your point groups, and it tells you a lot about them as in the combination. There's another system which is called the Schoenflies system, and that's indicated on the right here. That's used mainly by many chemists use it, people that deal in molecules but not in a crystal environment. And the C stands for cyclic, D is dihedral, T is tetragonal, O is octahedral, and S is rotoinversion. You'll see these in the literature, so this table will always give you a translation back to the Hermann-Morgan. So it's a very important table, and it literally goes from one to the other. Like 3 bar M is going to be D3D, and that's. Now we have a problem. The problem is that we want to put the information of a 3-dimensional object into 2 dimensions. We've come across this in our daily lives with the world. We want to put that into a 2-dimension. We don't want to carry big balls around with us. So we do that type of projection here. If we want to have X, Y, and Z, so we have some position here, X, Y, and Z. And if we want to project that onto this pink plane, we take a line and we put it from the point to the South Pole, and there it is. And then at the point where this pierces the plane, we put our point, and we color it a full color. We color it in, which means that we started out with a Z in the plus direction. We indicate that on our diagram here with the point in off the circle. That means it has a positive Z direction. And you can see over here, this is Y and X, and here is Y and X. And the Z is indicated here. It shows that the Z is positive by being a filled-in circle off the main perimeter. On the other hand, suppose you have a point X, Y, Z bar that is in the southern hemisphere. The point is located there. Then we can't draw a line to the southern hemisphere, but we can draw a line to the northern hemisphere. And again, where that pierces the surface, we can put a circle. We use a circle to distinguish from the top. If you have a circle, you're talking about Z bar. If you have a point, you're talking about Z. So now let's look at our crystal systems. So 3 bar, for example, the point stereographic projection would be if we want to go counterclockwise by 120 degrees, and then we go through the inversion point, we come out here. We go counterclockwise, and that's below the plane. Now we're below the plane, we go counterclockwise by 120 degrees. We go up above, so we're above the plane, and we get a plus. And we continue along that, and we fill in all of them. And when we leave this one, we can go counterclockwise here, and we come through the inversion point, and we're just back to where we started. So here are our symbol and our symbol and our point stereographic projections. Similarly, for the 4 bar, we go counterclockwise by 90 degrees, and then we go through the inversion. We go counterclockwise by 90 degrees. We come in through the inversion. You have to be really careful about that. I was going to edit that out, but I thought I'd leave it in just to show you how careful you have to be. So you go counterclockwise. I know all our clocks are digital. Counterclockwise by 90 degrees, and you come out here at below the plane. And so you continue on, and when you go here, you're going to end up just cycling around to what you started out with, and so the order is going to be 4 for 4 bar. So here we have the symbol and the point stereographic projection. And similarly for the 6 bar, we're going to go counterclockwise by 60 degrees, and we come out and come above the plane up there, and now we continue on and we find we get these 3 bullseye. Of course we have 6 points that we're generating, so the order is going to be 6, and whenever you see these bullseye effect, you're going to know that there's a mirror plane between in the plane of the computer or the plane of the board, whichever you're looking at. So here we have the mirror in the plane, which is indicated by a solid line all around the perimeter, and here we've made it really, really solid, and then here's the symbol for the 6 bar here. So whenever you have the 6 bar, you're going to automatically generate this mirror plane here, and here's the point. And here we put them all together. We've done them all. The only thing that's a little different here is these 2 different orientations of the mirror plane. We could orientate it along, say, the y-axis here, and we have the plus going to the change of handedness across here. On the other hand, if we put the mirror plane in the plane of the board, the plane of the computer, we create this bullseye effect, and that's what our symbol looks like. These are exactly the same monoclinic system. It's just down 2 different axes. Now let's look at a point group 2 over m, which is a point group of half the class, and it's a point group with multiple generators, and we're going to represent it by a function. So here we also have, here's our molecule for representation, and here's our function. The function z is equal to f of xy, x times e to the x to the minus x squared plus y squared. Now, this 2 over m is going to have a twofold, a mirror, and a generated inversion, and we can check all those out. First of all, we have the inversion point, the mirror, and the twofold, which we will look for. So to do the inversion point, we start out with point fx bar y bar, and if you put that into this equation, you can see we get x goes to minus x, and these are squared, so that the sign of that goes away. So we have this function is equal to minus z bar, so we have x bar, y bar, z bar, and here is our inversion point, and so any point x, y, z is going to go into a point x bar, y bar, z bar. So this this function has an inversion point. It also has a mirror, because if we go x, y bar, we're going to generate a z because the x doesn't change, and we have the z. Remember, Rufo's paw changed in the y direction, so here we're going to have a mirror is going to be located in the xz plane, and here's the y perpendicular to the mirror, and you can see the mirror goes through this mountain and it goes through this valley over here. We also have a twofold. The twofold is x bar y, which is going to give us a minus z, and here's a twofold coming out like this, and you can see if you rotate this figure around, you're going to have the mountain go into the valley, and the valley is going to come up to the mountain. So this function exhibits 2 over m symmetry. We have a lot of places we can apply these point groups to. Here's the multiplication table for 2 over m. You're going to look up the in the appendix for 2 over m, and you're going to see the xyz can be translated into the identity matrix. So you can have, for each of these elements, you can have the matrix, and then you put the matrix into your multiplication table, program the starter program, and it doesn't matter what the dimension is. The program will work for 2 dimensions or 3 dimensions, and will produce the multiplication table just the way you did it for your 2-dimensional exercise. And you can do the same thing for 222, the other half of the class. Okay, now for the 2 over m, here's our matrix generators, and here's our point and stereographic projections. It's called the crystal system is monoclinic, which I want you to remember. And here is the other orientation. This should be really perpendicular. It looks rather funny. Okay, and now we have the three-dimensional point groups with multiple generators. Another one, this is point group 3-2, which is the point group of quartz or alum, anhydrous alum. And another example of this would be a propeller, where you have a sort of twisted, if each wing of part of the propeller here is twisted in the same direction, you have a two-fold, so you have a three-fold sticking up and three perpendicular two-folds. And here is the multiplication table for that, and it's gotten exactly the same way. You look up 3-2, suppose you wanted to do that, and you look it up in the appendix, and you can produce it by the program in exactly the same way. So if we want to go from, here is the examples of the point stereographic projection and the symbol stereographic projection. Notice the Hermann Morgan symbol has just rotations in it, and that's and it has no mirrors in it, and that's carefully designed. So if you see just rotations, you're going to have a point group which all of the symmetry operations have rotations, so everything is colored red. So that's very convenient for the system. Now we're going to go to the 7 crystal systems. Well, what do we think of when we think of 7? Well, we think of maybe 7 days of the week, or possibly Snow White and the 7 dwarfs, which is just what we have here. So our 7 dwarfs can be represented by triclinic, monoclinic, orthorhombic, trigonal, tetragonal, hexagonal, and cubic. And of course, I am Snow White. So now we can put all of these together in a 3D point group tree, just like we did before. Please make 2 copies of the next slide and take out your colors and follow along with me on the first copy. This will be important because it will be part of Wednesday's quiz, which will consist of coloring this in the way in which I'm coloring it now. So what we're going to do is we're going to color, here's our point group tree, and we're going to color in the various systems. You're going to have them labeled here, and this is what I expect you to be able to do. So we look at, first of all, the cubic system, and the trick about the cubic system is it always has either a 3 bar or a 3 in the second position. The second position means we're going down the diagonal. So here we'll mark the cubic groups in green, and now we'll go to the hexagonal groups, and we'll mark them in magenta, and here are the hexagonal groups. And now we'll go to the tetragonal groups, and you can see they all start with 4 or 4 bar, and we're going to mark them all in yellow. And finally we have the trigonal groups, which start out with 3 or 3 bar, so we're going to mark them all in blue. And we'll come down to the monoclinics. Now remember, this is the monoclinic for half the class, so it's 2 over m, and we have 2 over m, m, and 2. Keep in mind that m is exactly equivalent to 2 bar. And then right in the middle here we have the orthorhombics. The other half of the class is 2, 2, 2, so you'll see the orthorhombics here. And then we have finally the triclinics. You don't have to use the colors that I've used, but you have to be able to understand where we're coming from in this exercise. Okay, now let's look at the individual systems. We'll start out with the triclinic system. The point groups are 1 and 1 bar, and here's the stereographic projections. We'll put them right here, the point projection. So here we'll have the point, and then we add the second point, and for our symbol we don't have any symbol for the identity for the 1, and the 1 bar has this little tiny circle, and this 1 and 1 bar is different. They're the operations for the generators. So unfortunately, the operation of the generator, or the operations and the name of the point group, is the same for 1 and 1 bar. That is just unfortunate, but you have to keep that straight in your head. So these represent the generators for 1 and 1 bar. It'll be clearer as we go up in the different systems. Now, half of you are monoclinic people. So here you're going to have your 2 over m. Here's your monoclinic, and you can see how there's a contribution from the mirror to the 2 over m, a contribution from the 2, and we join them together, and we also, that generates an inversion point right in the middle here. You can see this red goes to the blue, and the red on the top here goes to the blue on the bottom. Notice that this bullseye that I keep talking about indicates that we're going to have a mirror plane in the plane of the computer, the plane of the paper. So when we do our symbols, here's the mirror in the plane, and that's translated up here to the mirror in the plane, and here's the twofold. The twofold, we've had that before, and now when we do the 2 over m, we're going to generate this inversion point here, and we indicate by that little dot over there. And now we can see the generators a little more clearly. We can specifically set this up as 2y, generator for 2, for generator for m, and then if we combine those, we can use these 2 generators to generate the 2 over m. Now the other half of you have 2, 2, 2, which is in the orthorhombic system, and again we can see the 2, 2, 2. Notice these are 3 2s, so they're all axes. There's no mirror. The mirror is not mentioned at all, so that means that the symbol is telling you that you have that everything's going to be colored red. The MM2, once you have a mirror indicated there, you're going to have a blue to red change, and when we combine these two, we get these bullseyes, and you can see that when you combine, see the 2 mirrors here. We keep those 2 mirrors, and then we add this little mirror around the edge here. And again, over here, when we combine these 2, we add in an inversion point. And here's the generators associated with those various groups. Now I'm going to quickly go through the other systems. Here's tetragonal, and here's the point and the symbol stereographic projections, and here are the generators. We can do the same thing with the trigonal crystals. Here's the corresponding group here. You'll see certain structures that are similar. We won't go into that in this course. And then we have the hexagonals, and then finally we have the cubics. The interesting thing, one thing I find quite interesting about the cubics, you only have 2 generators for all the cubics, and there's some very interesting crystallographic reasons for that, of which we will go into right here. There are other things that we can indicate on our diagram, our tree, our point group tree, and this notice, of course, the point group tree on the cover of the book is the 3-dimensional point group tree. In this group, I've put the minimum number of generators. So here, all on the bottom here, you can see the 1 and 1 bar, 2 and m, 3 and 3 bar, 4 and 4 bar, 4 and 4 bar, and 6 and 6 bar, giving us the cyclic groups. And then the ones with 3 generators are 4 over mm, and 6 over mm, and then the rest of them are all 2 generators. This is mathematically very important, and you can pursue this at another time. Now let's do an interesting application, and that is in piezoelectric materials. In piezoelectric materials, we have dipoles here, and the dipoles are such that if you if you put a voltage across the material, then you're going to get a strain in the material. If you apply a force, then you're going to get a voltage coming across it. And one interesting application are these sneakers, so that when you put your heel down on the sneaker, you are pressing a piezoelectric material. It causes voltage to be generated, and that voltage turns the light on. So here you have the dipoles, the plus and minus dipoles lined up, and then they get squeezed, and then they produce the voltage. There are many, many applications, and I'd be open to any number of extra credit projects if you want to look into materials that are piezoelectric. Now, from a crystallographic viewpoint, you have to have a dipole in order to have a piezoelectric material. But if you add to a dipole an inversion point, you can't get a piezoelectric material, because if you put into this system an inversion right in here, you're going to get the plus going into plus or the minus going into minus. You can't get the plus going into the minus. Therefore, you cannot get a dipole cannot exist when you have the inversion point in here. So that means that the piezoelectric effect forbids a center of inversion. Now we can turn that around and make use of it, and we can see how we classify materials according to their symmetries. So let's look at a few definitions. We have the piezoelectric materials produce electricity when squeezed or placed under mechanical stress. Reversing the direction of the stress under tension reverses the sign of the voltage. There's a great variety of the amount of voltage generated under stress. And even though the piezoelectric effect may be theoretically possible, the effect is often so tiny that you can't even detect it. So it's really not very useful when under that particular type of material. And then currently the piezoelectric particles can be introduced into composites to control the ability of that material to dissipate mechanical or acoustical energy. A tremendous number of applications there, and you can look that up for extra credit if you'd like. And the addition of some functionally active components to composites produces a whole new level of material design. So that's very exciting. Now, on the crystallographic side of the picture, we have the centrosymmetric crystals are crystals which contain an inversion point. They are never, 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 never piezoelectric. The inversion point implies the impossibility of an induced dipole moment. Additionally, the cubic point group 432, though lacking an inversion point, cannot exhibit the piezoelectric effect because the symmetries in that point group cooperate to prevent an induced dipole moment. Very interesting proof, which I'll show you some other time. On the other hand, we have the non-centrosymmetric crystals, and they are crystals which do not contain an inversion point. If a crystal is to be piezoelectric, it must form in one of the non-centrosymmetric point groups, excluding 432. So now let's get your other copy, and we'll see what we can understand about how the point group tree will help us. Now we're going to follow along with your crayons here. Okay, so now let's go and mark our inversion point. Now if you look at all of the rest of these labels, there's no inversion point. There's no 1 bar anywhere here. The Hermann-Margolin notation does not give you whether it contains an inversion point. However, if you can look at your tree, you can tell immediately, because if the 1 bar is a subgroup, then that means that you can just follow it up here. So 2 over m has 1 bar as a subgroup, so we can color that in. And if we go up on the other side here, we can go up to 3 bar, and then we can fill in mmm, 4 over m, just follow it up, 6 over m, 3 bar over m, 4 over mmm, 6 over mmm, 3 m, m3 bar, and m3 bar m. These are the 11 central symmetric groups, and if you're going to look at piezoelectric effect, you also have to knock out the 4, 3, 2. Now I expect you to be able to do this, and to if you want to check, and does this group 4 over mm have a 1 bar as a subgroup? Well, you come down here, you come down there, you come down there, and there it is. So you're always able to trace that lineage out. Now let's look at a specific example. One of the most famous and strongest piezoelectric materials is barium titanate. Below and above it has a Curie point, and here's pictures of it below the Curie point and above the Curie point. Below the Curie point, there you have a dipole here, you have no center of symmetry. Above the Curie point you have a center of symmetry. Here's the information. We go from tetragonal to cubic. As we pass through the Curie point, we go just like say ice goes to water. It changes its structure as it goes through the freezing point. The barium titanate changes its structure as it goes through its Curie point. So it goes from 4 mm to m3 bar m. It goes from centrosymmetric no to centrosymmetric yes. And so you have piezoelectric below 120 degrees and no piezoelectric above 120 degrees. Let's go look at our filled-in table. We can see that here is the 4 mm barium titanate below the Curie point. You can see that this point group does not have 1 bar as a subgroup. You come down here. There's just no way to get over to this 1 bar. So now when you heat it up, it goes to barium titanate cubic, or m3 bar m, which does have a center of symmetry, and here's the pathway that it goes. You could think of it perhaps as adding a center of symmetry here, because 4 over mmm has a center of symmetry. Notice when I say the bar, you read it as 4 over mmm, and then you could maybe put a threefold down, add a threefold down diagonal, the 111 diagonal, for example, and come up to m3 bar m. So if you have an application of piezoelectric in barium titanate, you better watch your temperatures. If you're below 120, you're fine. If you go above 120, you lose that ability to detect anything about the piezoelectric. So this all comes into material designs. And here's an official picture of it. And then finally, I'd like to show you a ribbon picture of a myoglobin protein. And here's the porphyrin ring, and here finally are my parametric snails, and I threw in a mirror plane here, and there are problems in the back of the book about the parametric snail, and you can do that for extra credit if you wish. And finally, that's all for now, folks. See you later. Bye.